Hello everyone, this is Rakhi Kaushik and today we'll do quick revision of amines chapter. So let's start with the chapter. Now we'll start with classification and IUPAC nomenclature. So amines is a NH2 group. So we generally write it as RNH2 when it is aliphatic, and when it is aromatic we write ARNH2. When we write NH2 it is a primary amine. Now the first page of first paragraph tells that's why we are studying this chapter, because amines, they are a part of proteins, vitamins, hormones, polymers, dyestuff, drugs. So since they are part of so many things, so it becomes important. Novosin, it's a synthetic amino compound. It is used in anesthetic. Then Benadryl cough syrup is there. It is an antihistaminic drug. Then quaternary ammonium salt, they are used as surfactants. Diazonium salts, they are used in dyes. So we have a full class of dyes that we call it as a azo dyes, which has N double bond N. Okay, now in classification, we classify them as primary, secondary and tertiary amine. Primary is when it is NH2, secondary is when it is NH, and tertiary is when it is N. So you can see when we write it N, it means there are 3 R group attached to it. And how they are made, if you see the structure, we have done ammonia, NH3 in chemical bonding chapter. We know that nitrogen, it is in group 5, so it has 5 valence electron. So 3 valence electrons, they are used up in bond formation. So they make bond with H or R, and 1 lone pair left behind, that is called as non-bonded valence electron. So that is the lone pair. So this H, if they are replaced by R group, alkyl group, it can be methyl, ethyl, propyl or whatever, then we call it as amines. So when it is NH3, it is ammonia. Hydrogen of ammonia, when they are replaced by methyl, we call it as amine. If 1 H is replaced, we call it as primary amine. If 2 H are replaced, we call it as a secondary amine. And if 3 H are replaced, we call it as a tertiary amine. The angle is 108 degree. It is not 109.5 degree because of lone pair bond pair repulsion. We have done in Vesper theory in chemical bonding that lone pair repulsion is more than lone pair bond pair repulsion, than bond pair repulsion. So because of this lone pair, it pushes the bonds, and that's why the angle is 108 degree. And this nitrogen is sp3 hybridized. If we see the classification, as I told you, ammonia, if I replace this H with R, I get a primary amine. If I replace 2H, I get a secondary amine. If I replace all the H, I get a tertiary amine. So this is the classification. Now, if we see the name, we name it as alkyl amine. So amine, we write it as last. So it can be ethane amine, propane amine, pentane amine. And when it's a parent chain and NH2 comes in between, then we tell the position also where N is there. For example, if I make a long chain and I, like this one, and I put NH2 at second position. So I can say this as 1, 2, 3, 4. So butane 2 amine. Now remember, when we write butane, but because 4 carbon, and ane because single bond, and amine because NH2 group. Now we just skip this E because we have done it earlier also when the secondary suffix has vowel in it. So we just remove the E of alkane. So it is butanamine. This is how we write, and since this amine is at 2 positions, so we'll write it as butan 2 amine. We'll write it as butan 2 amine. And if more than 1 NH2 are there, then we write it as di, tri, tetra, this way it goes on. So nomenclature of primary amine is quite easy, but when we have a secondary amine, so for secondary amine, we write it as N. Like if you see here, now see this one, this is N ethyl. Can you see N ethyl methanamine. But when we write a IUPAC nomenclature, we write the smallest one with as N, and the longest one we take it as Me. So this is N-methyl ethanamine. N-methyl ethanamine. Why we write it as N-methyl? Because you can see methyl group is attached to N. And suppose if there are 3, then we can write it as, just choose any 2 because they all are same, they all have 1 carbon only. So it will be N-dimethyl because there are 2 methyl. So you have to tell the position where it is attached. So they are attached to N. So N-dimethyl methanamine. N-dimethyl methanamine. Okay, so you can see here, this is ethanamine. Now if I say replace this hydrogen with methyl group, so I'll say it as N-methyl ethanamine. If I replace both the hydrogen, then I'll write it as N-dimethyl. So if I replace both the hydrogen, then I'll say N-dimethyl ethanamine. So this way it goes. You can see here also. Now you can see there are 2 ethyl group attached to it, and the longer chain 1, 2, 3, 4 carbon will take it as a parent chain. So I'll say it as N-diethyl butanamine. Is that clear? So there are a few names that you have to remember, especially aniline. Aniline, the IUPAC name is benzenamine, but we use aniline a lot. So benzene with NH2 is aniline. The way, we remember toluene as benzene with CH3, phenol as benzene with OH, anisole as benzene with OCH3. So same way, aniline is benzene with NH2. And if one methyl group is also attached, we call it as orthotoluene or 2-aminotoluene, because benzene with CH3 is toluene. So at 2 position we have an amino group. So 2-aminotoluene. And same way, suppose if we have an aromatic group plus aliphatic. So you just see the smaller chain, CH3 is there. So it is N-dimethyl benzenamine, or you can write aniline also. It's fine. N-dimethyl aniline or N-dimethyl benzenamine. Now, question can be asked, classify the amines as primary, secondary and tertiary. It's an in-text question. How I remember is that when it is NH2, it is primary, when it is NH, it is secondary, and when it is N, it is tertiary. Now, in NCERT, the isomerism is not mentioned, but you can see the in-text question, tell the isomers as well as the IUPAC name. Since we have done isomerism in grade 11, some basic concept of organic chemistry chapter, so you can go through it. Now, if we say amines, they show position isomer. Position isomer in the sense I have a long chain and I can change the position of NH2 group, maybe from 1 to 2 or 2 to 3, like that way. Maybe at one time we'll put NH2 here, and in a second compound I can put NH2 here. So that is the position isomer. So we change the position of functional group. Now second is a chain isomer. Chain isomer is you can twist and turn the chain. For example, I can make this as N isomer. I can make this as isomer. Yes, keeping it NH2, or I can make it as a neo isomer. So this is the chain isomer. Then we can make it a functional isomers. So it shows functional isomerism. In functional isomerism, the same compound, I can make it as secondary or I can make it as tertiary. So that is a functional isomer. For example, I can make this, let me take this one. So this compound, maybe I can take 2 on this side and I can make this as N. H 1 2 3 4 5. Okay, so you can see now it was NH2, now it became N. Or maybe I can remove this and I can, this is the second isomer, secondary amine. I can make it a tertiary also. So you know what are isomers, that they have the same molecular formula but different structure formula, since they are structure isomers. So primary, secondary, and tertiary amines we can make, that makes the functional isomers, and it also shows metamerism. Now what we do in metamerism, we just change the carbon on both the side of amine group. So like if I have a secondary amine here, maybe in one isomer I have 3 carbon on this side and 2 carbon on the other side, or I can just move this carbon here and I can make this as 1, 3, 4. So 4 carbon here and 1 carbon here. So when we remove the CH2 group on both the sides of functional group, that we call it as metamerism. So this way it shows position, chain, functional, and metamers. These are the isomerism that it shows. Just go through this slide carefully. So now our next topic is preparation of amines. I always feel better to make flowchart like this to do any reaction. That helps in conversion also. So we'll do preparation by different methods. Now, I must have told you earlier also, whenever I have a hydrocarbon, I can put oxidizing agent and I can make it at alcohol. That alcohol also I can oxidize and make it as aldehyde or ketone, depending upon whether it's a primary or secondary alcohol. And on further oxidation, we get acid. And whenever we have an acid, I can put ammonia and I can heat it to make an amide. Amide is an acid derivative. Or maybe if I can make acid to CN, and then CN I can put water and make it as amide. So the reason I want you to write this chain is it helps in conversion. Sometimes we have to convert amine compound into non-nitrogen containing compound. Then this chain helps. So first reaction I can see in your book is reduction of nitro compound. Now if I have a NO2 group, for example, it can be aliphatic or it can be aromatic. Now, just you can observe here, it is NO2 and it is NH2. It means I have to remove oxygen and I have to add hydrogen. And we know that addition of hydrogen and removal of oxygen is a reduction reaction. So what we'll do is we'll do reduction. And you should know few reducing agent. We can use either nickel or platinum or palladium, or I can use Sn and HCl, or I can use iron and HCl. So it's up to you, you can use any one of it. And reasoning question can come that we prefer iron with HCl. So reduction with iron scrap and hydrochloric acid is preferred because FeCl2 formed, it get hydrolyzed to release HCl. So you can see when FeCl2 is made, it releases HCl, so there is no need to add further HCl. We need only small amount of HCl, that is only to initiate a reaction. So iron is cheap, we are adding HCl, but there is no need to add a lot of HCl because we just need small amount to initiate the reaction. It automatically converts to FeCl2, which get hydrolyzed to releasing again HCl. So that's why, whenever we want to manufacture anything, we always look at cost effectiveness also. And here, that's the reason one reasoning question can be framed here, that why we prefer iron and HCl over others. In organic chemistry, generally you get questions on name reaction, you get question on conversion, you get question on test, you get reasoning question. So this is the first reasoning question that can be framed. Now, next reaction I can see is ammonolysis of alkyl halide. Now, ammonolysis of alkyl halide, it means we are introducing or we are putting ammonia in Rx. Alkyl halide is Rx. So I'm writing Rx, this R can be anything, any alkyl group, or X can be the group 17, fluorine, chlorine, bromine, iodine. So we don't take fluorine, but it is iodine, bromine, and chlorine. Now the rate of reaction, if you see, Ri is more reactive, the order of reactivity of halide with amines, Ri is more reactive than RPR, then RCl. Okay, so we take ammonia, say primary ammonia, we put Rx. If we put 1 mole of Rx, I'll get R2NH. So I'll get a secondary amine. So I have ammonia, I'll put Rx, I get R2NH. If I put 2 moles of Rx, then this H will also be replaced by R. So I'll get R3N. And if I take further Rx, it means excess of Rx, I'll get a quaternary ammonium salt, that is R4N plus X minus. So what we are doing is we are doing ammonolysis of Rx. Now the drawback or disadvantage of this reaction is that we get a mixture of primary, secondary and tertiary amines as well as quaternary salt. That is a drawback, then again we have to separate them. So this question can be asked as a reasoning question. What is the drawback? Why we don't prefer this reaction? Because we get a mixture of primary, secondary, ternary and quaternary ammonium salt. Okay, but if I want to make only primary amines, as a major product, I can take excess of ammonia and less of R. If I take just 1 mole of Rx and more of ammonia, then I can get primary amine. Okay. And if I want to prepare tertiary amine only, then I can take more of R and less of ammonia, then I'll get the tertiary amine. And these salts that we get, say suppose if I get a quaternary salt, so free amines it can be prepared if in this I'll add strong base like NaOH. So I have R4NX and I put NaOH, I can get the amine. Okay, so 3 questions. First is disadvantage of this reaction. Second is how can we get only primary amine as a major product? And one more, what is the order of reactivity of halides? Next is the reduction of nitrile. Now nitrile is a cyanide group, that is CN. Common name is cyanide and IUPAC name is nitrile. So if I take any nitrile and I add a reducing agent like LiAlH4, or I can do catalytic hydrogenation. It means I can add either nickel or I can add sodium and mercury with ethanol. So any one of the things we can add, it converts into amine. Now remember, all the reactions that we have studied till now, we are not decreasing or increasing the number of carbon. So number of carbon has to remain same. So here it will become RCH2NH2. Okay, this reaction is very important reaction because we use this reaction in ascent of series. Whenever we want to increase one carbon, so for preparation of amines that contains one carbon atom more than the starting amine, we use this. I have a Rx, I add alcoholic KCN to it, I get ARCN, and you can see here by putting KCN we have introduced one carbon. Now this I can reduce to amine. Okay, so maybe I have one amine which is less than carbon, I can convert it to ARX by ammonolysis, then I can put alcoholic KCN, I'll introduce CN group to here, and then I'll reduce it. So this way is an important reaction if I want to convert or if I want to increase one carbon, ascent of series or step up series. Now next is amide, reduction of amide. So this amide we have, which is ArCONH2 or RCONH2. Now this can be ArCONH2, which is here. Can you see here? It is RCONH2, which is amide, which is an acid derivative. If I reduce this acid derivative by using LiAlH4 followed by hydrolysis, whenever we write number 1, number 2, it means I'll add LiAlH4, I'll get some intermediate. In that intermediate, if I put water, I'll get the product. So if I want to skip some step, we use this way. So I can reduce by putting lithium aluminum hydride, which is a strong reducing agent, and I'll get amine. So whenever I have a chain like this, suppose I want to convert alcohol to something, I can convert into amide, and then this amide I'll just reduce it, I'll get amine with same number of carbon, So you can see most of the reaction, whether you see this or this or this. So out of all these 3 reactions are only reduction reaction. So even if you know the reducing agent and you know what is happening, there is no need to learn these reactions. Now next one is a very important reaction, that is Hofmann-Bromamide degradation reaction. Why it is important? First, it is a name reaction. Second, it is a step down series. Now we have studied a lot of step up series, but very few step down series. So if I want to decrease one carbon, Like here we were increasing one carbon, but here we are decreasing one carbon. So what I can do is, whatever compound I have, suppose I have maybe hydrocarbon or alcohol or aldehyde or acid, I'll convert it into amide by following this chain. We have studied this chain in aldehyde ketose chapter. So I'll get an amide. Now in this amide, I will add bromine and NaOH. So bromine, Pr2 plus 4 NaOH, what I'll get is amine which has one less carbon. So basically I have removed this CO group. This CO group goes as Na2CO3, okay, sodium carbonate. So what I'll get is RNH2. So you can see I have reduced the CO group. That's why it is called as descent of series or step down series by one carbon. So it's very important because we have done hardly 2 or 3 step down series only. One is decarboxylation by putting soda lime, that is NaOH and CaO in the ratio 3:1, where we remove the CO2 group. And this is the next one where we are removing this CO of amide group. Hofmann bromamide degradation, step down by one carbon, very important reaction. One more name reaction is mentioned, that is Gabriel phthalimide synthesis. Now again it's a name reaction. It is used for preparation of primary amines only. Remember, this question can be asked. It can be a reasoning question. We use this reaction only to prepare primary amines. Only to prepare primary amine, that also aliphatic amines. Aromatic primary amines cannot be prepared by this method. So this can be another reasoning question. Aromatic primary amines cannot be prepared this method because aryl halide formed here. Aryl halides, they do not undergo nucleophilic substitution with the anion formed by phthalimide. So here when we get an anion, this Rx, when it is aryl, it does not undergo nucleophilic substitution. SN substitution, SN reaction with the anion formed by phthalimide. Let's see how this reaction happens. Though it appears difficult, but it is not at all. You just need to know what is the structure of phthalimide. So let's start like ahead. Suppose if I have a phthalic acid. Now we know it is an acid. So I put ammonia and I can make amide of it. I'll heat it. So what I'll get is phthalimide. Phthalimide. But when I strongly heat it, what I get is phthalimide. 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 So this is the phthalimide, which can be a starting reactant here. Now when you put KOH, you don't have to do anything. Just replace this H with K. Okay. Then you add RX. Now when you add alkyl halide, replace this K with R. Replace this K with R. Rest of the structure will remain same. Now you can see everything is happening here at NH. So first put KOH, replace this H with K, put RX, replace this K with R. Now after this, when you will put 2 NaOH, 2 OH, what will happen? H and H, these two H will go here and we get a separate product, that is a primary amine, and this ONA and ONA will attach here to get a sodium salt of phthalic acid. This reaction will come as such only, like prepare or just write Gabriel phthalimide synthesis if it will come. And 2 reasoning question can be asked. What is prepared by this reaction, that is aliphatic primary amines. Second, why aromatic amines cannot be prepared by this method. Now try to do this question. Write chemical equation for the following conversion. So CH3 CH2 Cl converted into CH3 CH2 CH2 NH2. So you can see you are adding one carbon and we are converting Cl to NH2. So you can do, we'll follow this path. I'll say this as a garden, you should know where to roam, yeah. So it is, you have CH3 CH2 Cl. So it means you have an alkyl halide. So first you will add alcoholic KCN or NaCN. What you will get is CH3 CH2 CN. Now you do reduction. So when you do reduction by adding LiAlH4, or maybe nickel, or maybe NaHgC2H5OH. Any one of these you will get amine. Same thing you will do for the next reaction. Now next question is to write the structure and IUPAC name of the amide which gives propanamine by Hofmann-bromamide reaction, and second is the amine produced by Hofmann degradation of benzamide. Correct. So the first one is butanamide and second is aniline. Do these conversions. Convert benzene to aniline, benzene to N-dimethyl-aniline, and ClCH2 whole bracket 4Cl to hexane 1,6-diamine. So first one we'll do nitration and then we'll do reduction. In second question we'll first do nitration and then we'll get aniline. We'll add 2 moles of Rx and we'll get tertiary amine. In the next question, we'll first add ethanolic NaCN. So we can introduce CN-CN group on both the side and then we can do reduction. Or directly also we can do ammonolysis. If it's changing from CH2 to CH6, then we have to introduce CN group. So we have to react with ethanolic NaCN. And if the number of carbon are same on both the side, then we can directly do ammonolysis. Now let's start with physical properties of amines and chemical properties of amines. So first, physical properties of amines. Now amines, because they have a lone pair of electron, they can make hydrogen bond. Okay. And since they can make hydrogen bonds, so lower aliphatic amines are soluble in water. We have done that all organic compound, they have a wonderful force of attraction, and the one those show exceptions, they have a hydrogen bond. Like alcohol also make a hydrogen bond. Okay, but the hydrogen bond of alcohol, since alcohol is more polar than amines, so hydrogen bond of alcohol are stronger than amines. So they are more soluble and they have a higher boiling point and melting point as compared to amines. Okay, and remember only lower amines are soluble because when the R part increases, then the non-polar part increases and then the solubility decreases. So higher amines are insoluble in water but lower are soluble. And if the reasoning question can be asked, you will say the lower aliphatic amines are soluble because of hydrogen bond. They make hydrogen bond with water. Now next is physical properties. We have hydrogen bonding. Now if I compare among amines, primary amines, they make more hydrogen bond than secondary than tertiary. Why? Because primary amines have more H, isn't it? It is RNH2. So it has 2 hydrogens, so it makes 2 hydrogen bond. Secondary amine has just 1 H, so it makes 1 hydrogen bond with water. And tertiary amine doesn't have H, so it will not make hydrogen bond with water. Yes, and that's the reason the hydrogen bonding is stronger in primary, then secondary, then tertiary. So this is how intermolecular hydrogen bonding in primary amines that can be represented. Now this hydrogen bonding affects the melting and boiling point because of hydrogen bond. Amines, they have a higher boiling point as compared to alkanes. So if we have to compare alcohol and aniline, amines and alkanes or hydrocarbon, so alcohol, they have a higher boiling point than amines, and then you can say you can take aldehyde ketones because they have a dipole-dipole interaction, and then hydrocarbons. And the reason, if they ask you, the reason is because of hydrogen bonding. See, standard answer is always there, either van der Waals force or hydrogen bonding in physical properties. And among amines, if they ask you, then primary amines, they have a higher boiling point, then secondary, and then tertiary. Why? Because primary make more hydrogen bond, then secondary, then tertiary. And suppose if among primary they ask you, they give you a few primary compounds and they ask you which one is most, which has the highest boiling point or something, then remember you will see the van der Waals forces. So more the number of carbon, because now It's all primary amine, isn't it? So more the number of carbon, more is the van der Waals force of attraction, so higher is the boiling point. Or lesser the branching, because branching decreases the surface area. So less branching, more surface area, more van der Waals forces. Okay, branching decreases the surface area as well as van der Waals forces. So this way, just write this line related to boiling point. Alcohol, higher boiling point, then amines, then aldehyde ketones, then alkanes. You can write the reason because hydrogen bond. Among amines, write primary has higher, then secondary, and then tertiary. And among primary, if they ask you just 1 or 2 carbon difference, then more number of carbon, more van der Waals forces, more is the boiling point. Now let's move to chemical properties. See, acidic character of acid and basic character of amines is very important. Okay, I have seen, most of the time I have seen question based on basic nature of amines. Now amines, if you see, it has a lone pair of electron. Because of this lone pair of electron, it is basic. Why? Because we say that electron rich are Lewis bases, because they can very readily give this lone pair of electrons. So they are electron donor. So electron donor, electron rich are Lewis bases. So amines, they act like a Lewis base. And how we can see it? Because it reacts with acids like HCl to make a salt. You know, we have done this reaction, acid plus base gives salt plus water. So since it reacts with acids to give salt, this proves that it is base. And what kind of base it is? It is a Lewis base. Why it is a Lewis base? Because it is electron rich. Amine salts, when we treat with base, we can regenerate the parent amine. This we have done just in ammonolysis also. And amine salts, they are soluble in water. They are soluble in water and they are insoluble in organic solvents like ether. So this way, by using this reaction, we can separate amines from the non-basic organic compound because they are soluble in water. See how we use these techniques to separate things. Now, sometime in exam, they give you a Kb or pKb value and they can ask you tell which one is most basic, which one is least basic, or arrange them in order of increasing or decreasing basic character. Then you have to check that the one which has more Kb, Kb is the
Base acid, base.
Is that clear?
Yes, ma'am.
Okay. Okay. इजी हो गया ना, नहीं तो एनसीईआरटी पढ़ के थोड़ा कॉम्प्लेक्स लग रहा था.
Yes, ma'am.
You're writing it, no?
Yes, ma'am.
Okay. ओके. ये लिख लिया था आपने रिया?
Yes, ma'am.
ओके.
Yes, ma'am.
चलो अब आगे
मैम एक्चुअली मैंने सिर्फ नोट्स बनाई है पहले, तो मुझे जो एक्स्ट्रा पॉइंट लग रहे हैं मैं वो ऐड करती जा रही हूँ.
ओके फाइन, दैट्स गुड. अपने हाथ के नोट्स की तो कोई मैच ही नहीं है मतलब ना.
Yes, ma'am.
So if I have to compare with aryl amines, I'll follow this order. So secondary will be more basic, then tertiary, then primary, then ammonia, then aniline with some electron releasing group at ortho para position. It can be any releasing group. It can be OCH3 or it can be R, and normal aniline or aniline with some electron withdrawing group. The withdrawing group can be NO2, SO3H, COH or halogen. So anything that withdraws the electron. Remember, the logic of basicity is just one thing. Anything that is increasing electron density on nitrogen will increase its basic character. and anything that is withdrawing electrons from nitrogen will decrease the basic character. Now let's check out some chemical properties. So that was the first reaction, that is the basicity of amines in chemical properties. Second is alkylation. Alkylation, just now we did that, we put RX and we can introduce R and R group to amines. Now next is acylation. Acylation, it means we are introducing a acyl group. Now what is acyl group? COCH3. So if I put acid chloride to it in the presence of base like pyridine, what will happen? Now suppose even if you don't know what will be the product, just think logically. Everything happens at functional group. Here we have a CO group and here we have a nitrogen which is electron rich. So it means I have to create some place for this electron rich side to attach. So CO bond is polar, oxygen is more electronegative. So this lone pair, this pi electron will go here, oxygen will become negative, carbon will become positive. Now carbon has created a space for this lone pair to come and attach. So nitrogen will go give its electron and will attach here. Since nitrogen has given its lone pair, so it will have a positive charge. Oxygen, since it pulled the electron, so it has a negative charge. Now to neutralize this compound, the hydrogen which is joined to nitrogen will give its electron and go as H+. And Cl which is joined to oxygen, this electron will go back and Cl will take this electron and will go as Cl-. So in the end, we get acylated product and we'll get HCl. Now, if you don't want to go in detail, it's not at all difficult. You just have to remove HCl and join these two compounds. You will automatically get your product. That's the only thing you have to do. And even the naming also is not difficult. See, what we say amide, isn't it? So if I take this as amide, which is an acid derivative, it has 2 carbon. So I'll call it as ethanamide. Yes. Now, if you see this nitrogen, there is one ethyl group attached to it. So I'll say N-ethyl ethanamide. Now, for example, suppose if I have 2 ethyl group attached to it, then I'll say it as N-diethyl ethanamide. Isn't that easy? Now this reaction, it is carried out in the presence of a strong base like pyridine, which removes HCl, so formed, and shifts the equilibrium towards the right side. So this question can be asked that why we add pyridine to it. The purpose of putting a pyridine is to remove HCl because pyridine is a base and HCl is an acid. So acid plus base makes salt. And if the reaction is reversible and we don't want it to reach to equilibrium, so we shift the equilibrium in the forward direction so that we can get more and more of product. Now similar reaction we have to make acetanilide. Now I want you to know the formula of acetanilide because it can be asked as a IUPAC or sometimes they can ask you convert benzenamine to acetanilide. Now you know the reaction but you don't know what is acetanilide. Then you'll be stuck. So what is acetanilide? It is N-phenyl ethanamide. N-phenyl ethanamide is called as acetanilide. And if this RCOCl is not R, it is AR. When it is AR, then rather than calling it as acylation, we call it as benzoylation. Why? Because we are putting a benzene group. Here you can see they all were ethanamide, propanamide, pentanamide, but here it is benzamide. It is benzamide. Now here this is the benzamide and CH3 is the side group. So N-methyl benzamide. So we are putting a benzyl group, so we call it as a benzoylation reaction. And to put a acyl group, we know that we can take acetic anhydride also, or you can take acid halide also. Now this reaction is a very, very important reaction. We call it as carbyl-amine reaction. The reaction is important because first it's a name reaction and second it is a test. So this is a test where we take primary amine. It can be aliphatic or aromatic. When we heat it in the presence of chloroform and ethanolic KOH, what we get is a foul smelling isocyanate or carbyl-amine. We call it as a carbyl-amine. Remember, it's a test, so observation is important. That is, it has a foul smell. And second, it is important that it is only given by aliphatic and aromatic amines. So a good test, observation, and a name reaction. So that's why it becomes 3 times more important. I have seen this reaction a lot of time in exam. Carbyl amine reaction. We can take, if I have to distinguish between primary aliphatic or aromatic amines or something else, maybe secondary amines or anything like, I can use this reaction. Okay. Now the second test can be with nitrous acid. Now when we take primary amine, we get a compound when we take primary amine and we add HNO2. So HNO2 is same as NaNO2 and HCl. We put it at the present at 273 to 278 Kelvin, or we call it as 0 to 5 degrees centigrade. We get an unstable compound which releases nitrogen gas. Now nitrogen gas is brown in color. It's a brown gas. So if it's a primary aliphatic amines, we'll get a brown gas. If it's an aromatic amines, so you know this is a diazotization reaction, we get benzene diazonium chloride, which is a very important product to make a lot of compound very easily. So we can use this reaction also to distinguish between primary and aromatic amines. Secondary and tertiary reactions, amines, they react in a different manner, which is not there in your syllabus. Okay, so this is another reaction. And the third test is with Hinsberg's reagent, that is benzene sulfonyl chloride. Benzene, this is sulfonyl, SO2, and this is Cl chloride. Now, if I have benzene sulfonyl chloride, which is also called as Hinsberg's reagent, when it reacts with primary amine, we get a compound which is soluble in alkali. Because it's a test, so observation are important. So it is soluble in alkali. Now, the question can be asked, why this compound is soluble in alkali? Because this hydrogen is quite acidic. So why it is acidic? Now, the next question, why it is acidic? Because of electron withdrawing nature of this SO2 group. So oxygen pulls the electron from sulfur, sulfur pulls the electron from nitrogen, and nitrogen pulls electron from hydrogen. So at the end, the weakest hydrogen has to leave as H+. And because of this electron withdrawing nature, this H is very acidic, and that's why it is soluble in alkali, because it reacts with base to give salt. While if we have a secondary amine, the compound formed is insoluble in alkali. Why it is insoluble in alkali? Because it doesn't have that acidic H. Can you see both are R? There is no H, no acidic H. So that's why it is insoluble in alkali. This is also an important reaction because it's a name reaction and it is a test to distinguish between primary, secondary and tertiary amines. Tertiary amines, they don't react. They do not react. So this way, primary amine, they give a compound which is soluble in alkali. Secondary amine, they give a compound which is insoluble in alkali, and tertiary amines do not react. So these are the sulfonamides, and this is how we can use this test to distinguish between primary, secondary and tertiary amines. Any doubt? Let's move to next important reaction, that is electrophilic reaction. We have done this reaction multiple times. In your grade 11th, we have done the entire mechanism. In RX reaction, in alcohol reaction, in aldehyde ketones reaction, in chapter. So many chapters we have done this reaction, and believe me, there is no need to learn these reactions. We have done bromination, we have done nitration, we have done sulfonation, we have done Friedel-Crafts alkylation, and we have done Friedel-Crafts acylation. Okay, 5 things we have done, I don't know how many times in your grade 11th and 12th. The only thing you have to remember is which one is ortho-para-directing group and which one is meta-directing group. Now, if you see aniline, aniline has a lone pair of electron. So it means it will give its electron to benzene ring. It means it will give a negative charge at ortho, para and ortho position by resonance. Now, when an electrophile will come, it will look for electron rich site. So it has 3 negative sites. So very quickly this will go and will attach at these negative sites. Now, the problem with aniline is that it is a highly activating group. It means it is so favorable. It wants to have electrophilic substitution because it has made this benzene ring very rich, very electron rich. Okay, now what happens when we do bromination? We add bromine to it. Rather than getting mono substituted product, we get tri-bromo product. Can you see 3 Br on all ortho and para side because it is electron releasing, so it has flooded benzene with the electron. It had made electron benzene as electron rich, especially ortho para positions, so very quickly electrophile can attack and make a tri-bromo product. But if I want to make a mono-bromo product, it means I have to decrease the activity. I have to make it less reactive. It means I have to divert this lone pair of electron not towards benzene but on the other side. Yes, so what we do is we do acylation. Just now we did the reaction of acylation. So we take maybe acetic anhydride or acid chloride in the presence of pyridine and we'll introduce COCH3 group. Now what is the purpose of putting COCH3 group? This lone pair, rather than going towards benzene ring, now CO bond is polar, oxygen will pull the electron, this will get a negative charge, this will get a positive charge. Now this carbon will say this nitrogen, please give your electron here. So this electron will go this side and we'll get N double bond like this. Now electron of this nitrogen, which was making benzene ring electron rich, is less available for benzene, isn't it? Now it has moved to the other side. So this way we have decreased the reactivity by acylation. We got this acetanilide. That's the reason I told you that I remember the name acetanilide. Now I can do bromination. I'll get only para product. Now once my work is done, I'll remove this acetyl group by adding acid or base. And I'll get a normal mono para bromo aniline. For any electrophilic reaction, I can do this thing. Let's take for nitration. Now when we do nitration, we do in sulfuric acid, H2SO4. We add HNO3 and we add H2SO4 at 288 Kelvin. Now H2SO4 is acid. So in a strongly acidic medium, the aniline, this aniline get protonated into NH3+. It becomes NH3+. Now this protonated aniline, or we call it as anilinium ion, it is meta-directing. Okay, and that's the reason rather than getting only ortho and para product, we get 47% of meta product also. Can you see? So this can be a reasoning question, why we get a meta product. The percentage is also quite high, 47% is quite high. Why? Because in a strongly acidic medium, we get an anilinium ion which has a positive charge and it is meta directing. That's why we get a meta product. Okay. Now, again, if I want to make a mono product, I don't want meta or something. So what I'll do is same thing. I'll do first acylation, then I'll do sulfonation. Suppose I'm doing here nitration. So I'll do nitration and I'll get a para product and then I'll remove this acyl group by adding H plus or OH negative. Okay, so we are decreasing the activity by acylation to get mono product. Now same thing with sulfonation. Now sulfonation, again we are adding acid, we get anilinium ion, we get a sulfanilic ion, that is the para product. Now here is, since it has both acidic and basic group on the same carbon, so this H can transfer here and we can get a Zwitter ion. Zwitter ion is an ion which has positive and negative charge of the same on the same compound, that we call it as a Zwitter ion. So we get NH3 plus and SO3 minus on the same compound. Now, one more thing you have to keep in mind, that aniline does not undergo Friedel-Crafts reaction. This question can be asked. Why? Because aniline is a base. And in Friedel-Crafts alkylation or acylation, we add Lewis acid, that is AlCl3, anhydrous AlCl3. The purpose of putting that Lewis acid is to generate an electrophile. Okay. Or we can say it acts like a catalyst. So this AlCl3 reacts with amine because acid plus base. So we don't get the desired product. Okay, so first, due to this, nitrogen of aniline acquires a positive charge and hence it becomes a strong deactivating group for the further reaction. So this reasoning question can be asked, why aniline does not undergo Friedel-Crafts reaction because it makes salt with the aluminum chloride used, which is alluvic acid, which was used as a catalyst to generate an electrophile. And due to this, nitrogen of aniline acquires a positive charge and hence it's a strong deactivating group for a electrophilic reaction. Okay, now next is diazonium chloride. Now this is again a very important reaction. We have done this I think 5 to 6 times in this book. If I take aniline, I do diazotization, that is I'll add HNO2 or you can say NaNO2 plus 2HCl at 273 to 278 Kelvin, or we call it as 0 to 5 degrees centigrade. I'll get benzene diazonium chloride. Okay, now this is an important product because we use this reaction to convert so many compounds very quickly. Okay, for example, if I take benzene diazonium chloride, I can add Cu2Cl2 with HCl to get ArCl, or Cu2Br2 with HBr to get ArBr, or CuCN with KCN to get ArCN. These reactions are called as Sandmeyer reaction. We have studied in RX chapter also. Or if I don't want to take these, if I want to take only copper and HCl or copper and HBr, I can convert it into ArCl or ArBr. This is called as Gattermann reaction. This also we have done in RX chapter. Or if I just want to introduce I group, then I just put Ki and I get ARI. Okay. Or if I want to put F group, halogen, fluorine, then I add HbF4, I'll get ArN2BF4 and I'll heat it, I'll get ARF. This is called Ball-Schiemann reaction. Ball-Schiemann reaction. Now, suppose if I want to convert this not to fluoride but to nitro compound, I add NaNO2 copper and I'll heat it, I'll get nitrobenzene. So you can see how quickly we are converting without using much of the salts or compounds. And if I want to convert to benzene ring, I can add H3PO2 plus water, or I can add ethanol, I'll get benzene ring. And if I want to convert to alcohol, I just put water and I'll get a phenol. Now the last topic is coupling reaction. Now we get an azo product. We have a full list of dye which we call it as a azo dye. Azo is N double bond N. Okay, so here what we do is we take diazonium chloride and with that we take multiple compounds and we just do little changes in these compounds and we get different colors. Now this reaction can be used as a test also, very important test. If I have to say test between phenol and something, or maybe aniline and something, or maybe phenol and aniline, we can do this test. So what we do is we take benzene diazonium chloride, we take phenol in the presence of base. What we get is an orange color. What we get is an orange color, and it's not that difficult. Cl of diazonium chloride and para H. Can you see phenol is here, OH is here at the para position, that H goes off as HCl and we just join these two products. And what we get is a orange dye. Same way, if I take aniline, same thing happens and we get a yellow color. So from the color we can come to know that which one is aniline, the one which gives yellow, and the one which gives orange is a phenol. It's a name reaction, it's a test, and it's a full list of dye. So it becomes 3 times important. It's an example of electrophilic substitution reaction. So this is how we have made a chart where we have introduced the preparation as well as diazonium salt, and you can see here I can convert any non-nitrogen containing compound into nitrogen containing compound even with less number of carbon when I want to go through Hofmann-Bromamide degradation, or with the same number of carbon if I want to just reduce it by LiAlH4 and get the amines with same number of carbon. And I can convert these into again back to the parent chain with non-nitrogen containing compound. Suppose if I have an amine, I put HNO2 at 0 degrees centigrade, I can just convert it into alcohol. Or if it's aromatic compound, I can go through by making diazonium chloride and then I can convert it into non-nitrogen containing compound. You can keep this open and try to solve NCERT back questions. So let's see the test of this chapter. We have done carbylamine test, which is given by primary aliphatic or aromatic amine, and the observation is foul smell. You need to know the reactions also for these. Then we have a HNO2 test, where we get a nitrogen, a reddish brown nitrogen gas when it's a primary amine. We get a benzene diazonium chloride when it is an aromatic amine. We get an insoluble oil when it's a secondary amine. And we get a clear solution when it's a tertiary amine. Then we have done Hinsberg's reagent test, where we get a compound sulfonamide which is soluble in alkali when it's a primary amine. We get a sulfonamide which is insoluble in alkali when it's a secondary amine. And tertiary amines, they do not react. If we have to distinguish between phenol and aniline, we can use azo dye test. We get an orange color with phenols and a yellow color with aniline. So that's it for today. Thank you so much for watching and have a nice day.